So the first three problems in this video ask us to sketch a graph of a logarithm kind of by hand without any transforming of a given graph. And the instructions ask basically, they say to graph the logarithmic function, first write the function in exponential form, create a table of values, plot the points, state the domain of each function. So to do part A of number 66, the original function in 66 is in logarithmic form, and it's kind of hard to graph a function if you're not transforming a given function that's written in logarithmic form. So I'm going to get it written in exponential form. To get a function that's in logarithmic form written in exponential form, we cross out the logarithm, we leave the equal sign and the base, and then we switch. The x is going to move to the opposite side of the equation. Similarly, the y is going to move to the opposite side of the equation. The x is going to become the only thing on the left side. The y is going to move to the right side, and it has to become an exponent because I'm creating an exponential equation. So what I'm going to do in part 66a is graph the function x equals 2 to the y, and every graph that I do, at least the first three graphs that I do that I'm not transforming a graph, I'm going to have a table of values, and in my table of values I'm going to put the same starting 5 numbers, but unlike normal tables, my starting 5 numbers are going to go in the y column. So the table that I'm going to graph for problem 66, just like the table you're going to graph for number 67, is going to have the numbers -2, -1, 0, 1, and 2 in the y column. To get each x, I'm just going to plug those numbers in for y. To get the first x, I'm going to go x equals 2 to the -2 power, changing the y to -2. That's going to be the same as x equals 1 over 2 to the second power, and that's going to be x equal to 1/4. So the first point that I'm going to plot is 1/4 comma -2. So 1/4 is about there. It's half of halfway, and then down 2. Next thing I'm going to do is plug in -1 for the x, or the y should I say. I'll get x equals 2 to the -1 power. 2 to the -1 power is 1 over 2 to the first power, which is 1/2. The second point that I'm going to plot is 1/2 comma -1. So 1/2 is about there, then down 1. Third thing I'm going to do is plug 0 in for this y. I'm going to get x equals 2 to the 0 power. And anything to the 0 power is 1. So the next third point I'm going to plot is the point 1 comma 0. They're starting to get easy now. Next thing I'm going to do is plug 1 in for that y and get x equals 2 to the first power. 2 to the first power is just 2. The fourth point I'm going to plot is the point 2, 1. Lastly, I'm going to plug in 2 for that y and get x equals 2 squared. And 2 squared is equal to 4. The last point I'm going to plot is the point 4, 2. It's a reasonably easy graph to draw if you've graphed logarithms before. Since we haven't, and this is our first logarithm graph, just like exponential functions, most of them had a horizontal asymptote at the x-axis. Most logarithms, unless they're shifted, have vertical asymptotes at the y-axis. And I'm going to actually draw that vertical asymptote in. Most logarithms have vertical asymptotes at the y-axis. I'll draw that with that in mind, and then I will talk about that a little bit. So the graph that I'm going to need to draw is going to look something like this, where it gets microscopically close to the y-axis, but it never crosses the y-axis. This is because if I extended this table up, and in my x column I had numbers like -3, and my y column, if I had numbers like -3, -4, -5, -6, this would give me 2 to the -3 power by plugging in that number for y, which is 1 over 2 cubed, which would be 1/8. If you look at the numbers, I see 1/2, 1/4, they'd go 1/8, 1/16, 1/32, 1/64. The x's will never ever be negative when I do my y's this way. In fact, to find the domain, which I need to do in part B of a logarithmic function, I need to take that into consideration. So this is done with part 66a. This is making a table of values and sketching a graph. To find the domain of my logarithmic function, it's pretty easy if you have the graph to realize that this graph starts at 0 on the x-axis and goes off to infinity. I would say the domain is from 0 to infinity. Algebraically, to find the domain of a logarithmic function if you don't have a graph, is you just set the argument of the logarithm greater than 0. To find the domain in problem 66, the argument is x. I'm simply going to take that x and set it greater than 0. That's actually what the domain is. That's the domain written as an inequality. If I want to change that to an interval, the interval that's corresponding to x is greater than 0 is the interval from 0 to infinity. Logarithms aren't defined for negative numbers, nor are they defined for zeros. As a matter of fact, just to show you real quickly what happens on my calculator, if I try to find the logarithm of a negative number, if I try to find log base 2 of negative 1, or log base 2 of negative 3, or even try to find the logarithm of 0, each one of these is asking a question that doesn't have an answer. This one is asking the question 2 to what power is negative 1. This is asking 2 to what power is negative 3. This is asking the question 2 to what power is 0. And 2 to what power can only ever be a positive number. This side is always positive, and it can never be a negative number. Each one of these is going to have no solutions or no nice solutions. So if I did this on my calculator to find out what the log base 2 of negative 1 is, and did the log of negative 1 divided by the log of 2, my calculator is going to tell me that the answer has an I in it. Logarithms of negative numbers are like square roots of negative numbers. They're imaginary numbers. Similarly, if I did this one, log of negative 3 divided by the log of 2, I'd get another number that has an I in it. If I scrolled over far enough, I'd see an I. Logarithms of negative numbers are imaginary numbers, and when I go to sketch graphs, I'm only graphing real numbers. So there isn't going to be a point on the graph that has an x-coordinate of negative 1 because its y-coordinate is an I. So all of these aren't going to be graphable. I think the logarithm of 0, if I do it, it actually physically gives me an error. To do the logarithm of 0 divided by the log of 2, I actually get a domain error. So when I go to sketch a graph of a logarithm, most logarithms will have a vertical asymptote at the y-axis because the domain of most logarithms is 0 to infinity. Logarithms are not defined, or they give you i's, or imaginary numbers for negative values of x. When I'm graphing, I don't graph imaginary numbers. I'm only doing a graph of real numbers. I don't know if that's the best explanation, but I'm going to keep going. Otherwise, I'm going to just dig a hole deeper than I just did. So give 67 a go. On the next page, I'm going to do problem 69 because it's a little bit messier. So to graph problem 69, what I'm going to do is rewrite problem 69 to handle problem 69a. To sketch a graph, I'm going to write this function so it's not in shorthand form. I'm going to write it as a log base e of x equal to y, or y equal to log base e of x. It kind of doesn't matter which side I have the y on. So to graph this function, the first thing I want to do is write it in exponential form. To write this function in exponential form, I'm going to cross out the logarithm. The e's going to stay low, the equal sign's going to stay where it's at, and I'm going to move the x to the right side and the y to the left side. When I move the x to the left side, it becomes on the same level as the e. When I move the y, it becomes the exponent. So this is the function that I'm going to graph. It has the same graph as ln of y equals to ln of x. And when I graph a logarithm without transforming, I use the same table for every single logarithm. I'm going to put in the x column numbers that I calculate, and in the y column, negative 2, negative 1, 0, 1, and 2. For each of these y's, I need to get a corresponding x. I'm going to use my calculator. I'm going to round to 2 decimals. because I don't know how to graph e so well. So the first thing I'm going to do is go e to the negative 2 equal to x, plugging in negative 2 for that. And then I'm going to go to my calculator and go second in ln negative 2 power. And I'm going to round that to 2 decimals. I'm going to say that's 0.14. All of these I want to round to 2 decimals. Since I'm going to round everything to 2 decimals, let me hit the mode button, go down to the second option and hit 2. That way it's going to round to 2 decimals. When I'm done doing this graph, I'll change the mode back to float. The second thing I need to do is plug negative 1 in for that y. I'll get e to the negative 1 equals to x. And on my calculator, I'm going to go second in ln negative 1 power and hit enter and get 0.37. Third one, I'm going to put in 0 for this y and get e to the 0 equal to x. I know that that's equal to 1, but if I didn't, I can go second in ln, e to the 0, and hit enter, and it tells me 1. Gives me the 2 decimals, because now it's going to give every answer as 2 decimals. Fourth value, I'm going to plug e to the 1 equal to x. I'm going to go second ln, e to the 1. And when I do e to the 1, I get 2.72. And lastly, I'm going to plug in 2 for that y and get e squared equal to x. So second ln e squared, and I get 7.39. I have all my y's, or x's. I'm going to go hit the mode button again, go down and get it off of 2 decimal mode, just in case I don't need 2 decimals in the future, by hitting enter on float. And so the float now is highlighted. And then I second and quit. Let me plot all these points. When I go to plot the first point, 0.14 is positive, but it's less than 1. It's really close to the y-axis and down 2. The first point I'm going to get is just to the right of the y-axis at negative 2. The second one, point 0.37, is about a third. So I'm going to go a third of the way between 0 and 1 and then down 1. And then easy points, 1, 0. 2.72 is about a little bit more, about 3/4 of the way between 2 and 3, and then up 2. And then 7.39 is just a little under halfway between 7 and 8. And then up 2. This 2.72 is supposed to be at 1. This point was supposed to be here. This is a mess up. It's supposed to be 2.72 up 1, and then 7.39 up 2. Again, for most logarithm graphs that you're not shifting up and down, left and right, the y-axis is a vertical asymptote, and that's going to be the case here. The graph should look just like that. This is a perfect answer for 69A. I can find the domain by looking at the graph. The graph stays right to the right of x equal to 0 and goes off to the far right edge of the x-axis. Its domain is going to be 0 to infinity. If I wanted to do 69B using algebra, the algebra defined the domain of the function y equals the ln of x is just to take the argument x and set it greater than 0. That's the domain written as an inequality, and that's the same as saying 0 to infinity with a round bracket on the 0 because the graph actually doesn't touch the y-axis. So I won't do 68 because I did your 69. On the next page, we'll move over and we'll do the last by hand graph. And then the rest of the graphs we're going to do are just going to be shifting using the left, right, ups and downs and reflections. So to do problem 70, to do part A, I'm going to write the function in exponential form. The initial function for 70A says y equals the log base 1/2 of x. And I'm going to cross out the logarithm. I'm going to leave the equal sign alone. I'm going to leave the 1/2 on the left side, on the right side in this case. I'm going to move the y to the opposite side and the x to the opposite side. When I move the x, it gets on the same level as the 1/2. When I move the y, it becomes an exponent. So the function I'm graphing is x equals 1/2 to the y. I should probably put that 1/2 in a parentheses because the 1/2 of the y applies to both the 1 and the 2. I'm going to use the same table that I did for the last two problems. So in my y column, I'm going to plug the numbers -2, -1, 0, 1, and 2. I'm going to use my calculator to get the x's. The first x I need to do is I need to go x equals 1/2 to the negative 2 power, just change that x to a negative 2. To do that, I'm going to go parentheses 1 divided by 2, up arrow, negative 2 power. My calculator is going to give me 4. The next x, I'm going to plug negative 1 in for that y and get 1/2 to the negative 1 power. So I'll go parentheses 1 divided by 2, up arrow, negative 1, and get 2. The third y I don't need my calculator for because anything to the 0 power is 1, so that should be 1. But I could have did 1 divided by 2, up arrow 0 on my calculator and got that 1. The fourth y I don't need my calculator for. 1/2 to the first power is just 1/2. My calculator is going to give me 0.5, which is probably better. But for the fourth y, I'd go 1 divided by 2, up arrow 1, get 0.5 or 1/2. The last y, 1/2 squared, plugging this 2 in for this, this is going to be 1 squared over 2 squared, which is 1/4. And I can plug in 1/4 or 0.25. On my calculator, if I did this, it's going to instinctively give me a 0.25. If I hit math and enter twice, it'll give me 1/4. I don't care if you graph with decimals or fractions, whichever is easier for you. On that last problem with the e's, I couldn't make the x's into fractions. It wasn't possible. So now I have my points. The first point is the point 4, negative 2. So the plot, that's easy enough. And then 2, negative 1, 1 and 0, 1/2 and 1, and then 1/4 and 2. Still, the y-axis is going to be a vertical asymptote. Unless you shift the logarithm left or right, you're not going to get a vertical asymptote other than the y-axis. So the graph's going to look something like that. So that's good enough for 70 part A. For the domain, this graph exists straight to the right of 0 on the x-axis. The domain is going to start at 0. It's going to get a round bracket at 0 because the graph doesn't touch the x-axis, and it goes off to infinity to the far right edge of the x-axis. The algebraic way to get the domain doesn't matter if the base is a fraction or not. The algebraic way to get the domain, you take the argument. So in 70b, I take the argument to find the domain and set it greater than 0. And that just tells me the same thing, that the domain is x is greater than 0, which is the same as the interval from 0 to infinity. You should give 71 a go, and the rest of the problems we're going to use shifting to do the graphs. So for 72 through 83, we're given a graph of y equals the log base 2 of x, or f of x equals the log base 2 of x, because function notation makes shifting easier. For 72 part A, for 72 part A, given this function f of x equals the log base 2 of x, I want to find f of x plus 2. That's easy enough. I'm just going to change that x to an x plus 2. And generally, when the x plus 2 was in a parentheses, we'd leave it in a parentheses unless the problem had an exponent and that x was plus 2 was going in an exponent, then you wouldn't really need the parentheses. But this is the answer to part A. That's fine. Now to state the domain. To do 72b, to find the domain of a logarithm, you take the argument and you set it greater than 0. So for this problem, the function is log base 2 of x plus 2. To find its domain, I'm going to set x plus 2 greater than 0 and get x is greater than negative 2. This would be a completely okay answer for part 72b. The domain of this function is x is greater than negative 2. You could also write it's the interval from negative 2 to infinity. This graph, because it shifted left, the vertical asymptote is going to also shift to the left. So I want to describe the transformation, and we know that an f of x plus 2 is going to move a graph to the left 2 units. So my transformation for part C is the graph is going to be shifted to the left 2 units. And now I'm going to sketch a graph, and I'm not going to do a freehand graph. I'm going to use the graph that's given and shift it. So the vertical asymptote that was at 0 for this is going to shift left along with every point. So when I go to do this graph, I'm going to take the vertical asymptote that on a typical logarithm graph is at 0, shift it to the left 2. Now I'm going to take every point and shift it to the left 2. This point is going to move left 2. That point's going to move left 2. Every point I'm just dragging it 2 to the left. And as I move the points 2 to the left, they start getting closer and closer to that asymptote. And so it's going to look something like that. Maybe not the perfect graph, but certainly good enough. So I just took every point in the given graph and moved it 2 to the left. That's all I would expect you to do. You could copy down the given graph, and when you go to do your part 73, that's going to be shifted to the 1. Just take every point and shift it left to the left 1. In terms of the graphing, I'm going to graph every one. If when you do your homework you don't graph every one, maybe you graph 73 but you don't graph 75, then you graph 77 but you don't graph 79. If you only do a few of the graph, that's fine. But make sure to do the part, the A, B, and C. Find the function, find the domain, and state the transformation. And then if you don't graph every one because you don't have a graph in front of you like I do to make it easy, that's completely fine. Alright, so I'm going to move on to 74. So in 74 part A, the graph that I'm given is f of x equals the log base 2 of x. And I want to find f of x minus 3. That's just going to be the log base 2 of x minus 3 with the x minus 3 in the parentheses. That's finding each function. That's the answer to part A. For part B, to find the domain of my function, to find the domain of a logarithm, you set the argument greater than 0. An okay answer for the domain of this function is going to be x is greater than 3, or you can write 3 to infinity. X is greater than 3 is same as 3 to infinity. For 7c, describe the transformation. Because I'm doing f of x minus a number, that's going to move the graph to the right. In this case, the transformation is going to move to the graph to the right 3. So the vertical asymptote that was at 0 is going to move 1, 2, 3 to the right and go to 3. That's why the domain is at 3 to infinity, because the graph is going to start at 3. Now I'm going to take each point and move it to the right 3, and this is going to get messy, but I'll deal with it the best I can. So this point I go 1, 2, 1, 2, 3 to the right. This point 1, 2, 3 to the right. This point 1, 2, 3 to the right. These 2 points are going to be just to the right of this dashed line. So this point is going to be a little bit to the right, and this is even going to be a little bit closer to that dashed line. So I took each point and slid it to the right 3, and I just drew basically the same shape. Again, if you don't want to graph every one of these, because really the best way to do the graph would be to make a copy of the graph that I gave you and then do the transformation to each point. If you don't want to do every graph, it's completely fine. 76 wants me to find f of x plus 1. That's a super easy function to find. The plus 1's not in the parentheses, so it's going to go after the function. So when I go to do 76a, the function that's graphed is f of x equals the log base 2 of x. To find f of x plus 1, the plus 1's going to go after the function because it's not in the parentheses. The plus 1 doesn't go in the parentheses. That's my find each function completely done. To do the domain, this is a tricky one. When I go to do the domain in 76b, the plus 1 is not going to impact the domain. To find the domain of a logarithm, you just set the argument greater than 0. And so the domain was either going to be x is greater than 0 or 0 to infinity for the domain. The only time the domain is going to not be 0 to infinity is if you shift the graph right or left. Or if you reflect it over the y-axis, I guess that might also change the domain, but might see that in a second. So that's done with part B. To do the transformation in part C, this plus 1 is going to move the graph up 1. So I'm just going to take each point and move them up 1. And for part D, I'm going to do it right on the graph. So each point, I'm going to move it up 1. Some points are easier to move up than others. So up 1, up 1, up 1, up 1, up 1. The points are still going to hover on that vertical asymptote. None of the points are getting moved to the left or right, so the vertical asymptote doesn't get moved to the left or right. It stays right where it's at. Every point just gets slid up one, but stays the same distance from that vertical asymptote. So I did again. It's not the most stellar graph in the world. If I needed to do more accurate graph, I'd make it on huge graph paper, and maybe I could do something slightly more beautiful. But just taking every point, lifting it up one, making the same shape. The vertical asymptote didn't get moved left or right, so the graph still had to just hover right to the right of that line. You only shift the vertical asymptote if you're shifting if you're transforming the graph by moving it left or right. All right, 78. For part A, to find each function, the beginning function is f of x equals the log base 2 of x. Because I'm asked to find f of x minus 1, and that minus 1's not in a parentheses, for the find each function, the minus 1's just going to go after the function. Because I'm not shifting the graph left or right, I'm just shifting it up and down, that's not going to impact the domain. The domain is still either going to be 0 to infinity, or what you get when you set the argument equal to 0, x is greater than 0. Both of those would be completely fine answers for the domain. Just setting the argument greater than 0 is perfectly fine. For part C, the minus 1 in this problem is going to move the graph down 1. That's how I'm going to describe my transformation. And in part D, I'm going to do the graph by taking each point and moving them down 1. So down 1, down 1, down 1, down 1, down 1. The vertical asymptote stays in the same place. The vertical asymptote only moves off the y-axis if you shift the graph left or right. So again, a decent enough graph, maybe not the best graph ever, but you'll never get the best one from me. Just a few more problems to do. Let me do your 81 because it's a little bit tricky and maybe I skip my 80. So for 81, part A, the original function is f of x equals the log base 2 of x. I'm asked to find f of negative x. That negative x, because it's in the parentheses, is going to go in the parentheses with the x. That's done with part A. Now to do part B, to find the domain of a logarithm, I set the argument greater than 0. So I'm going to set negative x greater than 0. That's really setting negative 1x greater than 0 because there's an implied negative 1 in front of the x. I'm going to divide both sides by negative 1, and I'm going to get x is less than 0. When you divide by a negative, you flip the sign. This fraction is still equal to 0. So my domain is going to be x is less than 0, or that's the same as the interval from negative infinity to 0. Negative numbers up to 0 are less than 0. When I go to describe the transformation, that's when we don't do so much. This is reflecting over the y-axis. So part C, I'm going to describe the transformation. I'm going to say it's going to reflect over the y-axis. And now I'm going to take each point and move it to the exact opposite side of the y-axis. This point looks to be 4 to the right of the y-axis, so I'm going to move it, make it 1, 2, 3, 4 to the left of the y-axis. This point is 2 to the right of the y-axis. I'm going to move it and make it 2 to the left of the y-axis. This point is 1 to the right. I'm going to make it 1 to the left. This is about a half to the right. I'm going to make it a half to the left. This is a quarter to the right. It's going to be a quarter to the left. The vertical asymptote didn't shift because the vertical asymptote only changes if you move it left or right. Reflecting it doesn't change the vertical asymptote in this case. So this is not the best graph, but it's the mirrored image of that over the y-axis. So something like that is completely fine. It should go straight down here and not kind of bump back out. Part 80, question 80 would reflect it over the x-axis. I won't do the problem, but I'll sketch a graph real quickly. To reflect this over the x-axis, this point that was 2 above the x-axis would go 2 below. This point 1 above would go 1 below. The point on the x-axis stays on the x-axis. This point 1 below goes 1 above. This point 2 below goes 2 above. And if I was graphing problem 80, it would look something like that. Its domain is still 0 to infinity. I keep making these things hook out, but they stay tight to the y-axis. The domain is still 0 to infinity, and the transformation's reflecting over the x-axis, and I graphed it already. And I didn't find the function, but that's okay. I didn't want to do the whole problem. So one more problem in this section, and this is the only one where I just can't shift it around because it's multiplying a function by a number. That's a non-rigid transformation, and what I'm going to need to do is multiply all the y's by that number. So for part A of 82, the initial function is f of x equals the log base 2 of x. To find 2 times f of x, I'm just going to put the 2 in front of that function. The domain is still going to be the same. You find the domain by setting the argument greater than 0. The argument is just x, so it's either going to be x greater than 0 or 0 to infinity. And the transformation in 82 is the tricky part. When we multiply by a number greater than 1, when it was a parabola, we can say it got narrower, but it's not really you won't really see the narrower, so we're just going to say it gets stretched. Every point's going to get stretched away or pulled away from the x-axis. So the transformation, we're just going to say it's stretched. Now, to do my table, I'm going to use the same x column. The x column that I'm given is 0.25, 0.5, 1, 2, and 4. But for the y's, I need 2f of x. So I need to multiply each one of these numbers by 2. So I'm going to go negative 2 times 2, which is negative 4. Negative 1 times 2, which is negative 2. 0 times 2, which is 0. 1 times 2, which is 2. And 2 times 2, which is 4. So the points I'm going to plot are 0.25, negative 4. So 0.25 and negative 4. I probably could do it on this graph. 0.25 and negative 1, 2, 3, 4. And then 0.5, negative 2. So 0.5, negative 0.5, negative 1, negative 2. 1, 0 still stays 1, 0. And then 2, 2 instead of 2, 1. So that point gets stretched away from the x-axis. And then 4, 4 as opposed to 0.42. So each of the points gets just kind of stretched out. They get pulled further away. If they're on top of the x-axis, they get pulled further up from the x-axis. If they're below the x-axis, they get pulled further down. That's what we say they get stretched. The vertical asymptote didn't switch, though. Again, this graph just stays and hovers on that y-axis. So give 83 a go, and that will be the end of this section.